Welcome to my channel. This is PS. I hope you will learn something from this video. Stay focused.
Let's begin with these definitions. Please take note. Pressure gradient is caused by conversion of some pressure into energy that is used up by the fluid, while it flows inside the pipe. The problems that we will be discussing are the adiabatic frictionless nozzle, adiabatic frictional flow, convergent-divergent nozzle, and isothermal frictional flow. Here is the diagram of the different processes. I got these from the textbook. It is very important for you to understand this. You can pause the video if you want. In the next slides, I will be explaining this further. From reservoir, denoted as Pi, the gas will undergo isentropic expansion to Po. Gas is now in stagnation condition. Then, gas will flow adiabatically to P1, the discharge condition. This process is called the adiabatic frictionless nozzle. From reservoir, gas undergoes isentropic expansion to stagnation condition. Then it flows adiabatically to P1, called as the throat. It flows again adiabatically to P2, the discharge condition. As you notice, the path of flow diverges as the gas exits, so this is called the convergent-divergent nozzle. From reservoir, the gas flows directly into the discharge of the pipe, and the flow is isothermal. This is called the isothermal frictional flow. The frictional flow is due to the presence of the long pipe. From reservoir, gas undergoes isentropic expansion to stagnation condition. Then, it flows adiabatically to P1. P1 is termed as the discharge with respect to the nozzle. An entrance with respect to the pipe. Then it flows adiabatically to P2, the exit of the pipe. Remember, that the presence of a pipe causes the flow to be frictional. So this process is the adiabatic frictional flow. Now, I will be giving you the equations that we will be using for each process. Let's start with adiabatic frictionless flow. The conditions of the gas in each section is defined by pressure, temperature, velocity of the gas, and Mach number, others are density and mass velocity. For stagnation conditions, the velocity here is zero. Take note that stagnation conditions are the conditions that would be obtained by isentropically decelerating a gas flow to zero velocity. Now, here are the equations. For isentropic expansion, and for adiabatic flow. I also included the basic equations that you need to take note of. Let's proceed to sample problems. You can pause the video to read and understand the problem. For stagnation conditions, the velocity here is zero. Take note that stagnation conditions are the conditions that would be obtained by isentropically decelerating a gas flow to zero velocity. The problem asks for the pressure of air at the location where air velocity equals the speed of sound. What do you think of this? How can we relate the air velocity with the speed of sound? That's right, Mach number. If the ratio of air velocity is equal to the speed of sound, the Mach number will be equal to 1. And when Mach number is equal to 1, the condition is choked, can also be called sonic or critical. And critical conditions are characterized by asterisk conditions. So the equations for critical conditions are given as follows. And for isentropic expansion, our equations are. Now, solving for critical pressure, we have the equation. But we need to solve for PO first, so we have another equation for TO. Substitution for required values, we have critical pressure equals 1.1796 MPa. Now, for critical temperature, we have 300.99 Kelvin. And for Mach number at reservoir conditions we have 0.40. And that's it for the discussion about adiabatic frictionless nozzle. For adiabatic frictional nozzle, convergent-divergent nozzle, and isothermal frictional flow, follow the second part of this video.